Hi, everybody. How's the audio? People can hear me? Yep, I'm seeing thumbs up. Great. So my name's Corbin. I work downtown, not super important, except that it has nothing to do with this talk. I firmly believe in the open door policy, so for any reason you want to walk, just go for it. I'm cool with it. Also, I prefer questions as you have them, so that you don't forget them. So if you have a question, put up your hand, and I'm happy to take it. So as stated before, I'm Corbin. You don't need to know RPython or Monte or Llvm when coming into this talk. You just have to be a Python person. That's who I'm aiming at. If you don't know compilers, then that's probably not going to hurt you that much. But just for, for me, who here does not know what a compiler is, at least a little bit? One person. Okay. Couple people. So a compiler is a program that takes a string that has some kind of internal opaque structure and produces some sort of data structure, usually some kind of machine file or binary file. So it can be something that takes, say, my description of slides and produces a PDF of my slides. It could also be something that takes, say, a Python program and produces a bunch of effects on a computer, an interpreter. These slides are a little creaky because they are a little short notice-y. So the one thing that you will need to know is that an AST is an abstract syntax tree. So it's a tree, a data structure, that represents the code of a language, but in an abstract idealized form. So it means that we're usually not manipulating strings. We're usually manipulating references and relationships. Other than that, oh. Wow, this slide made it in. Thank you to Alan Short for convincing me to do this. It's kind of been 2.5 years, and I don't think I would have done it without him. Thanks to Mark Miller, Kevin Reed, Doug Crockford, and the other original implementers of the E language for writing a whole bunch of papers. Special thanks to Emily Dunham and Mike Cooper for coming into the channel 2 years ago and working on stuff. And a special thanks to Dan Connolly for making awesome documentation, which is not part of any of these slides. So, where I am in the Python community, I'm kind of on the edge. I dabble a lot in Twisted and PyPy. Are there any Twisted users in here? Oh, much more than I would have expected. Are there any Twisted users in here who don't already know me personally? That is more than zero. I'm kind of surprised. Cool. Yeah, so Twisted, if you don't know, is an incredibly robust networking library that is relatively unused within the Python community, but there is a small dedicated group of people that hack on it. And how about PyPy? Are there any PyPy users here? Couple, cool. So for those of you that don't know, PyPy is an implementation of the Python language in Python. This might sound a little silly, but what's not silly is that it's easily the fastest implementation, routinely beats other Python implementations on benchmarks. I highly encourage people to check it out. In fact, this is actually a source of constant sadness for me because people tend to not use Twisted despite it being, at least to me, obviously the best answer for doing networking stuff. And people don't use PyPy despite it, again, obviously to me, being the best Python implementation. But that's okay because I know that people have different preferences and there are reasons to not use Twisted or PyPy, even if I kind of work to make sure that you don't have to have objections to using great libraries. So part of the reason that Alan and I built Monte is because we wanted to take away people's choices. Specifically, we didn't want people to be able to choose not to use Twisted and not to use PyPy. We thought that that was a little silly. So the Monte language has networking power that is kind of like having Twisted always at your fingertips. And it's also fast because we built it using the same toolchain that PyPy is built out of, which is a library called RPython. That's what I'm talking about today. So, also, am I going too fast? Am I losing people yet? Nope. Great. Okay, I will go faster so I can lose you all. That was a joke. Sorry, I had breakfast this morning, so I am just on the ball. Okay, we're going to get into the slower slides. So what is RPython? This is actually a really tough question. Every time we ask this question, and every time we attempt to answer it, we end up pointing out things that people usually don't think about. So the PyPy team officially says RPython is a restricted subset of Python amenable to static analysis. And this is a good starter description. RPython is very much like standard Python. If you are used to writing structured Python in large code bases, say 20,000 to 200,000 lines of code, then RPython's style will make a lot of sense to you. It's mostly built out of standard Python classes and standard primitive Python objects, lists, ints, dicts, strings, etc., that are structured in a very clean hierarchy, Java style, usually about 4 to 5 classes to the module, usually about sometimes there's a parent class and a couple kids, but usually there's either no inheritance or single inheritance. Very, very simple, very, very pared down. What's important is that the restrictions that we place on ourselves when we write RPython are not just restrictions to make our code more readable or more modular, but they're also restrictions that allow the RPython toolchain to statically analyze and deduce properties of your program. This is something that has historically been near impossible for Python, and the RPython toolchain is built out of an effort to do this. Unlike other systems such as Python 3.x type annotations or NumBa, NumXpr, that family of tooling, RPython does not require any annotations to your program. In fact, RPython is designed to take typical, yes? So libraries like NumBa or NumXpr, features like the type annotation system, which was introduced in Python 3.2, 3.3, I'm not sure. These allow you to add some additional type information and execution information to your program, but they come at the cost of having to alter the code that's in your program to have special imports or declarations from those libraries. So, for example, NumBa requires that you put a decorator on every function that is going to be run through NumBa's optimizer. Python 3 type annotations require you to put an extra type annotation after every single argument, stuff like that. And RPython automatically figures out this kind of stuff without having to be guided. It takes typical things like, for example, isInstance. I know don't use isInstance in most code, but in RPython, isInstance actually turns into a type discrimination check. So it actually guides the type information of your program. My partner in crime, Alan, has a much more colorful description. He says that RPython is OCaml with very odd syntax and a very odd standard library. I can't really argue with this. Are there any ML users in here at all? No? Oh, one? Okay. ML, or meta language, is a big family of statically typed languages that are designed for building interpreters, compilers, meta languages. ML literally means meta language. OCaml is something in that family that has a lot of the same features as RPython. It has objects, it has modules, they combine in certain ways. It has automatic type inference that flows throughout the program. This means that discovering the type of anything is relatively easy. It's defined even if you didn't write it syntactically. You don't have to declare that something's an int. The program, the compiler knows that it's an int. The standard library of RPython is very strange. It's called rlib, and inside rlib you find all kinds of strange things like a bunch of tools for doing machine arithmetic with machine-sized integers. There's tools for low-level memory management, for garbage collector details, all kinds of stuff that seem very, very strange from the typical Python author's point of view, but they are indispensable if you're going to write something that is a low-level interpreter or compiler. So RPython is very much geared towards writing interpreters. This third bullet is my personal description. RPython is a toolchain that can translate carefully crafted Python packages into highly efficient low-level code. Typhon, which is my Monte implementation, or any other RPython package, these are typical Python packages. They're usable untranslated as is. You can run them on top of more or less any Python, including CPython. But they can also be translated into a very efficient low-level executable. However, I am going to say that RPython is not easy to use, and honestly, I don't think I will ever use it outside of the specific task of writing interpreters for languages. It is arduous. A lot of people show up in PyPy, the PyPy IRC channel, asking if it's possible to take an a non-RPython program whatever they've written, their web app, for example, and translate it using RPython for a speed increase? And our usual answer is no. Please don't do that. It's a lot of effort, and we're not prepared to do it. Things like Flask and Django are not even close to being RPython compatible. So it's a serious undertaking, and you will have to be prepared to lose a lot of things. Python programmers are very used to things being incredibly polymorphic, incredibly dynamically typed, dynamically named, etc., and you have to give up almost all of this when you're using RPython. It really is, when I write RPython, I feel like I'm writing Java or Haskell or OCaml. I don't feel like I'm writing Python, which is fine, but you have to be aware of what you're getting into. However, there is a very big boon to using RPython, which is if you write an interpreter that is RPython compatible, the RPython toolchain can give you a JIT compiler, an incredibly performant and efficient, powerful executable for your language at a steep engineering discount. I can't say for free because it's not free, you do have to put in some work, but as a point of comparison, it took me about 2.5 years to build my, my JIT. It took the V8 and Hotspot teams in their heydays also about 2.5 years. And they didn't have one person. They had about a dozen people on each of those teams. So that's a really big discount in terms of person years, you know, order of magnitude. It's pretty great. So digging in a little deeper, when you write a Python program and translate it using RPython, first your program is imported, and then it's transformed from Python into a much simpler form that has all the types figured out and that has all of the flow figured out. I realize that the word import there might seem a little disingenuous. I'm being very precise here. You know how in Python when you type import from some package and it runs a bunch of code at import time and then gives you a Python module? RPython actually uses standard Python machinery to do the import. So pretty much every single RPython interpreter has either a little amount or a large amount of metaprogramming magic that happens at import time. And after everything's imported and the metaprogramming magic is finished, then RPython analyzes what's left. And so this ranges from, so in Typhon we use this to automatically generate doc strings and help strings for objects. In Topaz, which is Alex Gaynor's implementation of the Ruby language, in RPython, he uses it to generate method stubs. So the logic of figuring out how many arguments go to a method, that kind of thing, whether or not it needs named arguments. He does that. The PyPy team goes one further, and they actually have a very fancy thing called an object space that is this magic metaprogramming wall that dynamically translates between high-level Python types in PyPy at the user level, and low-level RPython types at the interpreter level. And this is very confusing because they both appear to be Python. It took me more than a couple months to be comfortable with it. I'm still not quite comfortable with it. It's very magical in PyPy. If you stuff like naming a variable with an underscore at the beginning completely changes its semantics, that kind of thing. It's fun. I don't recommend lots of metaprogramming magic, but it's there if you need it, up until you're finished importing. And then RPython figures out all the types of everything. It makes sure that every variable has a known type. It figures out any references that need to be resolved. If there's any dynamic flow stuff, any kind of strange exception handling, it figures that out as well. So Python exceptions have a relatively magical type system, I like to think. You know, there's exceptions and errors and base exceptions and all kinds of stuff. And most of that's available in RPython, but RPython has to figure out exactly which exceptions you are and are not handling. So it can do proper things like make sure that, say, a key error turns into a crash after translation. You want that key error to turn into a crash. You do not want it to turn into an invalid memory access. That would be bad. And if you are a lucky person, you will occasionally be able to put some code on PyPy that causes it to segfault. It happens occasionally. It's pretty rare these days, but it's possible because most of those exceptions are erased away. So the translation is pretty serious. It's pretty involved. And then two things are stapled on. So the first thing is the GC, garbage collector. I'm probably going to be saying GC a lot. Garbage collector, who does not know what a garbage collector is? Any hands? Couple hands. Great. So a garbage collector is a chunk of code that is usually part of your runtime in your high-level modern language, and it takes care of memory management for you. It deals with basically anytime you need to get memory, anytime you need to let go of memory, the garbage collector is there to help. Garbage collectors are traditionally written as tiny little C libraries that are clipped on in an afterthought to your program. RPython lets you write the garbage collector in RPython, and it attaches it to your program without you having to notice. Additionally, the garbage collector, since it's also RPython, is imported, transformed, simplified, statically analyzed, and statically flowed, which means that it's optimized with the rest of your program, but you're allowed to pick it at compile time, which is pretty cool. So, if you don't like any of the half-dozen garbage collectors that come with RPython, you're free to write your own. It's a documented process and one that the PyPy team goes through about every 2 years when they realize that some new white paper has changed their paradigms. Literally right now they're working on something called software transactional memory. If in 2 years you come back and you hear a talk on that, it's because they finally finished. I'm excited. And then there's a JIT. By JIT, I mean that there is a just-in-time compiler. Typical compilers are what's called ahead of time. So you feed the compiler some data, it translates it into some kind of machine code, it gives you the machine code ahead of time. A just-in-time compiler waits until right before you're actually about to execute the code, or in RPython's case, after you've executed the code a bunch of times. It sees what happened while you were running that code, what kinds of types were nearby, what kinds of actions were taken, and generates efficient machine code representing the precise action that was taken at runtime. This might sound silly, but it's very fast. This is how Java goes fast. This is how PyPy goes fast. This is how JavaScript in your browser goes fast. If you're using Firefox, you're using a JIT for JavaScript. If you're using Chrome, you're using a JIT for JavaScript. This is pretty popular technology. So RPython's JIT is based on a couple annotations that have to be written by hand, and I'll explain that. But in exchange for writing, an extra 10 lines or so into your program, you magically get a JIT compiler, which is as correct as your interpreter and is more or less functioning independently of the interpreter. What I mean by that is that it has its own logs. It can be introspected and analyzed independently of your program. It uses a common semantics and syntax, which is based on RPython semantics and syntax, not the syntax and semantics of the language that you're interpreting. Put another way, and I'm kind of sorry that I didn't have a slide for this, the JIT is not about your high-level language that you wrote in the RPython interpreter. It's about RPython and RPython's understanding of what your interpreter does. So the JIT operates on RPython's types instead of your types. This sounds maybe pedantic, maybe a little silly, but the end result is that the JIT is generic, and you don't have to worry about whether or not the JIT got something correct. If your interpreter got it correct, then the compiled JIT code will also be as correct. And then finally, RPython generates a couple of optimizations that you might expect a compiler to do. It tries to remove some memory allocations. It turns if expressions, or sorry, not if expressions. They're not expressions in Python. I'm sorry, I've been doing like 5 different languages this weekend. If blocks, if statements. There we go. If statements, when you have a tree of them, you might think, man, I really wish that Python had a switch case statement. RPython automatically tries to find situations like that and generate them for you. So a lot of times we will have very, very stupid code that says if this, else if this, else if this, else if this, and RPython will turn it into a switch statement, mostly for sanity. And then it emits an executable. There are a bunch of other tools that do the same thing, more or less. It's worth examining them because these all are capable of producing JIT compilers, and I did consider them before going ahead and staking my my engineering time on RPython. So the first one is Llvm. I would be remiss if I didn't mention it. I know that I've only listed negatives here on the slide. I should mention the positives. Llvm is incredibly portable. It is incredibly simple as far as compilers that fully describe machines go. And the amount of effort required to write an optimization in Llvm is pretty low. Llvm is clearly meant to compete with GCC, and it shows. In addition, Llvm provides the garbage collector and optionally the JIT, which are pretty core here for going fast, right? However, and you can go look at the PyPy guys' FAQ for more detail on this. They've tried to use Llvm as a backend. 5? Okay. They've tried to use Llvm before. It hasn't gone well. A combination of mediocre control over what the garbage collector does and very poor JIT technology has led to it just not being a great fit. Additionally, writing C++ drains my soul. So that's an important thing to keep in mind. I am a Haskeller, so I did consider just writing things in GHC Haskell. GHC is an amazing platform to develop on. The big problem that I had with GHC is that its speed cap is relatively low. If you write efficient Haskell, then your thing will go fast, but only up to a point, and getting beyond that point is very difficult. And I thought that I could probably blow past that, that cap pretty easily with other technologies. Additionally, mutation is unbearably hard in Haskell. Specifically the kind that we had, so it was a non-starter. I did get about halfway there though. Writing bare or not embedded here style C++ and making a handcrafted JIT. This is what every JavaScript JIT does. It's a popular approach, I guess, if you have the engineering power, but reading, writing, and maintaining it is so hard that, once again, soul draining, no thank you. Finally, I have to mention Truffle. Truffle is awesome. You're probably not going to hear about it anywhere else because it's not well spoken of outside academic circles. Truffle is a Java library. You describe your language using Truffle. Truffle comes with a JIT. It is very fast. There's a recent paper by, I think, Stefan Marr that showed that Truffle is competing with RPython quite well in terms of speed and simplicity. It wasn't very mature 2.5 years ago. If it had been, I might have been writing in it, and I might have been at some Java conference instead of some Python conference right now. If you've ever wondered, what it's like to make slides in only 2 weeks, this is what happens. You decide, I know, I'll make tombstones. This is a terrible idea. Tombstones are compiler diagrams. The way it works is that on the bottom, you have what the compiler is running on the platform. And on the top, reading from left to right, you have what your source language is and what your result language is. So the old Monte compiler that we use for bootstrapping was written in Python, and it goes from Monte to Python. This is how we got started. The RPython translator is written in Python, and it goes from RPython to an executable. I'd kind of had a dream that maybe this would, answer people's questions forever, and I'm seeing a lot of bamboozled faces, so I'm very sorry for this. I'm also even sorrier for this one. This is this is my day-to-day workflow. So I can either run Typhon untranslated. I run it on some Python implementation. It takes mast, which is our internal format, and generates executable effects. It's an interpreter. And then I can translate it, which you can see with this composition of tombstones that is so pretty and also so opaque. And finally, there's proof that I'm not good at LaTeX. So I realize that I'm doing iffy on the time here, huh? Another 5. Okay, cool. Well, let's see if I can do 5 slides in 5 minutes. Five pieces that might be interesting. The AST loader. We don't have a parser. Parsers are hard. Parsers are unreasonably hard. Who's a parser pro in the room? Okay, great. Parsers are hard. So instead of parsers, we didn't do parsers. We have a separate compiler that's written in Monte, which is way easier, and then we just dump a tree that doesn't need to be parsed onto disk, and then we reload it. Simple, but I wanted to add this slide. Internally, inside the virtual machine, we compile everything into another lower level virtual machine. This is mostly done because I wanted to, I think. This is part of how we go fast. We take our abstract syntax tree, which does things like look up names based on their name, which is such a silly and antiquated concept, and instead we look up names based on an index of some flat list that we've generated, what's called the flat closure approach. This is very straightforward to do mechanically, and while I was doing it, I did some more things, and we ended up with bytecode. Bytecode's very simple, much simpler than Python. No loops, only one test, true, false, or exception. And there's a mini stack for exceptions. RPython has exceptions, so we piggyback on that. It's very nice. Seriously, how many times have you wanted to have exceptions in C? Nope. Like so many times? So many times? Yeah. Okay. Exactly. Well, we have exceptions in C, basically. So the Bytecode Compiler is incredibly derpy, incredibly simple, based on an older concept called small caps, which is for a language called E, which you should all go read up on and then be very confused. That's my recommended way to get into E. Also the bytecode, internal to Typhon. This is something that I think CPython messed up on. CPython's bytecode is external, it's written to disk, therefore people depended on it. We don't, it's only in memory, so we can change it as needed and we don't have to have an on-disk format. Our object model is incredibly simple. We have one root object. I called that class object because I have no imagination whatsoever. Here I'm calling it root, which might have actually been a good name. Monte's object model is there's a bunch of objects and you don't get to know their types. So right here we have a bunch of objects and their types largely don't matter. We had to implement a lot of different runtime objects, which is not a big deal, except there's a lot of typing. And then the user-defined objects, there's only one type of those, but there's a lot of them. They are most of what floats around in the system, so most of the code gets concentrated there. How to make a JIT. I actually covered most of this. The JIT looks for loops in the code. When it finds a loop, it traces what the loop does, then it compiles it to machine code, and does it all invisibly. Oh, yikes. I should have rushed to this slide, and then I should have just spent 30 minutes on this slide. It would have been so much better. You have to annotate once at the head of every loop that you want to JIT. Typically, this is your user level loop. So if you have some kind of while loop or for loop, you mark that. If you're, for example, PyPy also marks things like regular expressions, which are implemented as a little mini machine. Those are also JITted. Some things you have to fix. Sometimes the JIT looks inside something that it shouldn't look inside, and you have to mark it as don't look inside. Sometimes the JIT needs to look inside something, but the JIT will never look inside a function that has a for loop or a while loop, because it could lead to code explosion. So you have to mark those as safe. Sometimes you want to mark things as elidable. Sometimes you might want to mark things as constant. If this seems all like silly details, it is silly details. The JIT still works even if you don't do any of this stuff. This is just to make it go even faster than it already does. This slide, I think, is from entirely the wrong talk. RPython does have an FFI if you need an FFI. Does anybody use CFFI in here, maybe? A couple people. Cool. Made by the PyPy team, so you know it's good stuff. RPython also has an FFI for C. In RPython, it's called RFFI. It's the same model as CFFI, except it's at compile time, so it's slightly denser. It violates every single safety guarantee that Monte has built into it, and Monte's a very high-level, very safe language, so it's only used sparingly. My favorite library to pick on is libping. Libping is great code. It's well-maintained. It has only a security problem every couple years, and it decodes pings. That's not good enough for Monte. Either your code has to do something that's truly amazing and magical, like libsodium, where it does magical things to memory, or it has to be like libuv, where the benefit is so massive that we are willing to take security problems, even if they do happen. I zoomed through this so that I could get to the slides where I say, should you use RPython? And then the slide where I say questions. So should you use RPython? Yes. If you're writing an interpreter and you want it to go fast and you don't want to write Java or C++, use RPython. It is easily the best tool outside of what's in the Java and C++ ecosystems. RPython's competitors, the ones I listed above, consider them. Maybe they're what you want instead. So, questions? Please. Yes. I really highly doubt it. The same IEEE 754 semantics are present in RPython and work just as well, but actually writing stuff in RPython is a little bit of a pain. And honestly, given that NumPy support is starting to make its way into PyPy more and more by the day, I would seriously consider sticking with the NumPy code that you already have and trying to use PyPy. Cool. Yes? Okay. Yeah, so regular expressions and actually all the way up to the peg formalism can be implemented as relatively simple, small machines that only go forward. And it turns out that they always take the same steps the same time for most situations where the regular expression is constant, but the input isn't. So they put a JIT marker at the top of enter the regular expression, and it unrolls each iteration of the regular expression. And the result is a chunk of compiled code that steps directly through strings and has the state machine fully embedded. So white paper term to look for is partial evaluation. It's kind of a minefield, but there's a lot of good stuff out there, including some free books if you like. We good? Great. If you have any more questions, I'm cool with hallway stuff, so just come up and talk to me. Otherwise, thank you so much.